standing on a silent, sun-drenched bridge of land, only to watch it crumble and slip beneath the rising Pacific waves. This is the forgotten history of a landmass that once held together the southern hemisphere before being pulled into the dark abyss. Around 80 million years ago, it actually happened. Most of this expanse is now gone. It sits hidden beneath the Pacific Ocean, its true scale invisible to the naked eye. Only 6% of this continent remains above sea level today. New Zealand and New Caledonia are simply the highest peaks of this submerged giant. We have lived on the surface of a puzzle we did not realize we were solving. For decades, the scattered ridges and plateaus were viewed as isolated geological accidents. Now, the evidence demands a shift in perspective. We are looking at a continental mass that was stretched, thinned, and drowned by the shifting mechanics of the planet. The question of why this occurred and how we finally mapped the abyss reveals a fundamental layer of our Earth's history. To map this abyss is to reconcile the definitions of continental crust with a landmass almost entirely hidden. The first hurdle is the threshold of existence itself. There is no central authority to label a continent, so recognition depends entirely on assembling enough evidence to force a change in the map. We look for specific granite suites, crustal thickness, and clear geological boundaries. We examine how millions of years of tectonic stretching pulled the continent apart without destroying its essential structure. The mechanism involves heat, thinning crust, and the slow adjustment of height relative to the abyssal seafloor. Yet we lack a singular record of its final descent. The truth is buried in stratified sediment cores that act as a high-resolution archive of changing water depths. These layers record the transition from dry land to the dark ocean floor. We must now identify the exact evidence required to link those cores to the wider tectonic story. The investigation begins by defining the boundary between our continental block and the surrounding Pacific crust. To map the submerged silhouette of an entire continent, we must dismantle the assumption that land masses are defined by sea level. The work requires a rigorous dissection of the rocks themselves. We verify whether these hidden plateaus possess the distinct chemical fingerprints of true continental crust. Beyond the bathymetric scars of the Cato fracture zone, the physical record holds the keys to this transition. We test why this vast territory remains mostly below the waves, examining the precise moment of thermal decay that pulled the continent downward. Each layer of data reconstructs a history previously fragmented into isolated ridges and basaltic flows. Our investigation follows the path from tectonic rifting to the modern drill ships that pierce the sediment archives. We are building a map of a world that never truly vanished. We look past the water to recover a lost chapter of the planet's crustal history. In 1995, geophysicist Bruce Luyendijk introduced the name Zealandia as a shorthand for this vast, sunken domain. While it encompassed the exposed peaks of New Zealand and New Caledonia, the term was not a claim of discovery, but a structural invitation. Before this, geologists cataloged ridges and plateaus as disparate features, lonely fragments scattered across the seafloor. Luyendijk's label forced researchers to compare seismic data across the entire Southwest Pacific, shifting the focus from individual formations to the underlying crust. Scientists began to ask if these bathymetric rises were merely cousins in proximity, or the surviving summits of a unified foundation. If these features were pieces of one whole, the traditional map of our planet was incomplete. Consequently, every isolated ridge became a potential data point, and every deep-sea survey was reinterpreted through the lens of a larger system. The search for the continent shifted toward a deeper prehistoric origin point. Before the Pacific swallowed the land, it existed as the eastern edge of the supercontinent Gondwana. Granite roots anchored a vast, interconnected landscape. The geology here tells a tale of proximity. Zealandia stood shoulder to shoulder with Australia and Antarctica. They shared a single, unified crustal architecture. "80 million years ago, this connection fractured as the rifting process tore the margins apart. As the gaps widened, the internal geometry of the land began to change. Tectonic forces pulled the crust, stretching it thinner until it lost its buoyancy. Scientists debate the state of the surface during this separation. Did a continuous, dry bridge persist for millions of years, or was this land already breaking into isolated, archipelago-like chains? The physical record remains buried deep, and we lack a clear view of the timeline for when the dry land dipped beneath the waves. To map this transformation, we must trace the precise path of that ancient severance. The investigation's route is established, and we will now isolate the submerged shape to test whether the rocks themselves confirm a distinct history. To move from the route to the physical evidence, we look at chemical fingerprints trapped in granite roots. The first requirement is a definitive classification. We must establish a threshold for what constitutes a continental block. Current conventions lack a singular, binding authority. Recognition depends on convergent, evidence-based metrics published by the scientific community. We examine crustal composition, elevation, and distinct geological continuity. These criteria distinguish a single entity from a scattered group of unrelated rises. If our data confirms these continental markers, the existing map of Earth demands a fundamental revision. The search for these markers begins with the name itself. Scientists needed a term to unify these submerged fragments into a testable hypothesis. The label emerged as a direct response to a fractured understanding of the Southwest Pacific. We focus on how that name transitioned from a simple convenience to a rigorous geological category. This transformation turned a loose map of ridges into a singular, targetable model. Scientists stopped viewing New Caledonia as an outlier and New Zealand as a lone island chain, instead treating these summits as anchor points for a submerged province. To function as a continent, the landmass must demonstrate consistent crustal thickness across its entire span. This requirement forced a shift in methodology. Researchers no longer relied on the shape of a coastline to define the land, mapping the deep sea foundation instead. By measuring the speed of seismic waves through the crust, they detected the distinct, slow signal of granite roots. This density signature confirmed that the seafloor here was not volcanic debris but ancient continental material. It provided the mathematical threshold needed to separate a default continent from a fractured collection of islands. Yet, this new definition created an immediate geographic problem. To confirm the continental limits, they had to isolate where Zealandia ended and the Australian margin began. The line of separation sat hidden beneath the water. A mere 25 kilometers of distance defines the proximity between Australian and Zealandian crust. Seen from above, the gap appears negligible. Yet the Cato Trough functions as a definitive geological interruption. This feature drops to a depth of 3,600 meters, with a floor composed of dense oceanic basalt rather than continental rock. This distinct crustal composition identifies the trough as a sharp tectonic divider between the Australian plate and the hidden continental block. While the surface suggests a continuity of land, the underlying materials prove the two sides remain geologically distinct. Identifying this boundary requires looking below the sea surface, where the physical nature of the crust overrides the illusion of proximity created by the map. These indicators serve as the primary evidence needed to isolate where Zealandia ends and the Australian margin begins, providing the clarity required to confirm the limits of a submerged continent. Across the Cato fracture zone, the ground tells a story of lateral violence. Here, 150 kilometers of right lateral strike-slip movement scars the deep crust. These vast blocks did not simply drift apart. They ground past one another like tectonic teeth. As the Tasman and Coral Seas tore open, this displacement redirected the stress of a fragmenting continent. It linked spreading centers into a single kinetic chain. This fracture is not the singular engine of separation. It acts as a measurable piece of a much larger global puzzle. We track how the margins deformed under this pressure, revealing the mechanics of a breaking world. The shear motion explains why the continental edges look disjointed today. Yet, the deeper story lies in what rests beneath the fracture itself. The vertical drop into the abyss marks a sharper divide than surface geometry suggests. We must look toward the floor of the trench to understand the true break. The depth of the void tells us everything about what was lost. Frames used. Cato fracture zone shear map, tectonic displacement diagram, spreading center linkage seismic profile of the fracture epithets used. Kinetic chain, tectonic teeth, breaking world, abyss floor. Deep crust scar, lateral violence. Its floor is composed of thin, dense basaltic crust, marking a true tectonic rupture. The ocean basin here acts as a physical barrier separating distinct continental masses. Proximity of the surface margins matters far less than the composition of the seafloor between them. Seismic readings confirm that continental crust does not stretch indefinitely across this gap. Instead, it terminates abruptly against a sharp oceanic boundary. We are mapping a collision of different crustal signatures. This transition records the final violent stage of tectonic separation. If the crustal bridge were continuous, the continent would remain unbroken. Because the gap is filled with volcanic rock, the rift is complete. This trough serves as the ultimate geological arbiter of where one continent ends and the next begins. Yet, the mere existence of this volcanic window leaves a critical question regarding why the separation distance appears so deceptively narrow when measured from above. This oceanic interruption forces a reassessment of the regional tectonic architecture, revealing how seismic density mapping and basaltic floor analysis provide a clearer picture than the surface visual. Beneath the basaltic floor analysis lies the sharp crustal divide, confirming that the tectonic boundary diagram is not merely a model, but a reflection of the profound deep crust scar. The lateral violence inherent in the catastrophic cross-section demonstrates that the breaking world does not leave clues on the surface, but hides them within the kinetic chain of the abyss floor. The thin strip of the catastrophe holds the definitive proof. The seafloor drops 3,600 meters into a basaltic abyss. This deep, scarred floor is composed entirely of oceanic crust. It functions as a tectonic wedge, separating the continental masses of Australia and Zealandia. These landmasses may approach within 25 kilometers of each other at the surface. Yet, the crustal composition between them tells an immutable story. A continent requires granite, thickness, and stability. The trough lacks all three. Because this oceanic floor exists, the two landmasses are geologically distinct. Proximity is merely a geographic accident of the modern map. The true boundary is hidden deep in the dark sediment of the trench. This division is not a clean, static line. It was forged by grinding forces that shifted the crustal blocks sideways over millions of years. How that lateral motion carved the fracture zone and complicates the continental boundary remains the next piece of this investigation. It marks a distinct boundary where tectonic plates forced the crust into a new geometry. By mapping these scar tissue lines, geophysicists track how the continent physically detached from its neighbors. The 150 kilometers of right lateral shift acts as a reliable guide to these past movements. This displacement links spreading centers across the Tasman and Coral Seas, carving a path for the separation of the continental blocks. We see the faulting today as a clear bathymetric break, but it reveals the cumulative work of ancient shifting plates. This motion explains why the continental edges look disjointed on modern charts. It proves that the rift was not a clean, singular break, but a series of overlapping adjustments over millions of years. We must now reconcile this horizontal shearing with the vertical reality of the seafloor itself. The total depth of the trench dictates how we perceive the divide. The 3,600-meter floor is basalt. It is the oceanic crust that defines the true limit of this continent. Below the crushing weight of the Pacific, the seafloor changes its nature completely. Here, the continental margin abruptly terminates. Geologists monitor this transition by mapping the density of the seabed. Where the thick, buoyant rock ends, the deep ocean floor begins. The gap is narrow, yet it reveals a stark, permanent separation. We are reading a signature carved into the crust itself. This is the final, measurable edge of a hidden province. The investigation now shifts toward the very roots of the land. We must determine why such a vast foundation stayed submerged for tens of millions of years. The history of its descent lies trapped in deeper, ancient strata. Beyond the cold basalt of the seafloor, the deep structure holds a different story. We look past the oceanic crust to the samples recovered from the submerged margins. Here we find the chemical signature of the continental crust itself. Embedded within this hidden domain are granites from the Jacquerie Suite, dating back between 490 and 505 million years. They are Middle Cambrian in origin. These granites serve as a definitive marker for a long, stable continental ancestry, proving this region is not a transient volcanic pile erupted from the seafloor. Instead, they demonstrate that this massive, submerged landmass was once a default ancient extension of the continental interior. Yet identifying these specific rocks is only the start of our problem. We must determine how these ancient granites fit into the broader evolution of the continent. The question remains, how exactly do these ancient internal markers align with the total crustal architecture of the submerged block? These granites serve as geological anchors, their mineral composition matching the signature of the ancient Gondwanan core. They confirm a crustal history independent of the younger volcanic chains found elsewhere in the Pacific. Age alone does not define a continent. These rocks must align with the sheer depth and thickness of the underlying crust. Researchers map this continuity through seismic wave velocity, looking for dense granite foundations beneath the surface sediments. Without this granite base, the region would simply be a series of disconnected, submerged arcs. Instead, the chemical fingerprint of the Jacquerie Suite confirms a stable, thickened crust that spans from New Caledonia to the Campbell Plateau. It behaves as a buoyant platform that refused to be subducted during the opening of the Tasman Sea. Identifying the foundation is only the first step. Scientists still need to read the environmental history stored in the layered seafloor cover. The next investigation requires a drill string to reach through the water column and into that hidden, stratified archive. The drill ship Joida's Resolution maneuvers above the Tasman frontier. Between July and September 2017, the International Ocean Discovery Program launched Expedition 371. The crew targeted 6 specific locations across the submerged shelf, dropping a drill string through 4 kilometers of Pacific water. The steel pipe bit into the seabed, pulling up cylindrical cores of sediment. These tubes act as physical time capsules. Each layer of mud and fossil-rich clay records the environment of a different epoch. These cores bypass the limitations of sonar or seismic waves, providing direct access to rocks that were once deep beneath the surface and are now within our reach. Scientists are looking for proof of subsidence by searching for fossils that thrive only in shallow, sunlit waters. If those shells appear in deep sea sediment, they indicate a landscape that once sat near the surface. The drill reveals if this region stood as dry land or a drowning archipelago. The data contained within these layers will determine when exactly the continent began its descent. The steel casing bites into the soft, white ooze of the Tasman floor. Inside this pipe, the planet holds a record of its own decay. These cylinders of clay and skeletal remains act as archives of depth. Microscopic shells trapped within the layers change in species as the environment shifts from shallow lagoons to deep, sunless abyssal plains. Each centimeter of core records a measurable loss of elevation. By correlating these fossil transitions with seismic profiles, researchers pin down when specific plateaus succumb to the sea. The data forces a rewrite of the continent's life cycle. It reveals that subsidence was not a singular event. Instead, large blocks dropped at different times and rates. Mapping these localized sinks creates a timeline of the continental surrender. These cores are only the beginning of the mechanical puzzle. If the crust remains continental, something pushed it to the brink of failure. The engine of this transformation lies in the fires that pulled the land apart. Between 105 and 85 million years ago, the foundation fractured. Intense tectonic pulling tore at the eastern edge of the Gondwana supercontinent. Zealandia and West Antarctica were stretched thin across a vast, unstable interior. This was not a simple snap or a clean break. Crustal sections attenuated like pulling heated wax. Lower density rock was forced to compensate for the widening gaps. Heat flooded the base of the crust from the mantle below. Buoyancy vanished as the material grew brittle and thin. Faults crisscrossed the stretching block in a complex overlapping web. This initial stretching set the stage for total isolation. The continent was weakened long before the final rift opened. Each zone of attenuation acted as a structural point of failure. The question remains how this process shifted the continent across the globe, moving it from high southern latitudes toward its modern position. Frames used: stretched crust diagram, heat map of mantle flow, animation of rifting faults, reconstruction of Gondwana split, epithets used: tectonic fracture, attenuated foundation, structural failure, brittle crust. The continent did not merely drift northwards in a straight line. Reconstructions track its southernmost reaches, climbing from 80 degrees south latitude toward 50 degrees south. This journey spanned 100 million years of erratic plate motion. The path was not a steady migration. It involved complex internal rotations and shear deformation as the ancient Gondwana margin unraveled. As the crust pulled away, it was subject to intense warping and tectonic twisting. These forces dictated the final orientation of the submerged blocks we see today. Understanding how Zealandia rotated against the shifting Pacific floor requires more than just mapping current positions. It demands a precise model of how regional faults and oceanic ridges forced the continent to bend as it migrated away from the Antarctic pole. These motions suggest the sinking was never uniform across the entire mass. Localized regions responded to these stresses differently. Future models must account for this uneven tectonic load if we are to see the full shifting architecture of this drowned province. Frames used: rotating plate reconstruction, latitudinal shift animation, shearing crust diagram, suboceanic topography model, epithets used. Drowned province, erratic migration, tectonic twisting, internal deformation, shifting architecture. This tectonic history once existed as a collection of isolated data points. Researchers gradually synthesized these fragments into a unified record of crustal change, now captured by the 2023 GNS Science Reconstruction Project across 15 distinct maps. These models follow the continent from 98 million years ago through to the modern day, relying on magnetic anomalies, mapped fault networks, and the chemical signatures of ancient crustal blocks. Reconstructions anchor to paleomagnetic constraints, balancing recorded plate vectors against the shifting geography of the Southwest Pacific. These maps function as calculated hypotheses rather than photographic archives of a forgotten past. Where data gaps persist, the models project probable paths of seafloor spreading and plate drift. We can now visualize how internal rotation and crustal stretching shaped the region we inhabit today. Yet, the models only hint at the hidden costs of this geologic shift. Determining how early, sustained extension finally triggered wide-scale subsidence requires a deeper look at the specific tectonic sequence itself. To determine how early sustained extension triggered wide-scale subsidence, we examine the specific tectonic sequence itself. Between 105 and 85 million years ago, the land groaned under internal tension. Seafloor spreading drove a permanent wedge between Zealandia and its Gondwanan neighbors. Separation, movement, and drowning were distinct, sequential events. Plate boundaries shifted, tugging the continental block northward from 80 degrees south to 50 degrees south over an age of tectonic rotation. As the continent shed its heat, it settled lower into the mantle. Isostatic forces dictated the slow descent of once-high plateaus. Deformation warped the edges, while the cooling lithosphere pulled broad stretches beneath the encroaching waves. The final map is the product of this long cooling decay. 15 reconstructions connect these isolated remnants into a singular, cohesive history. These maps reveal the continent not as a static block, but as a fluid entity. Before this synthesis, researchers analyzed ridges and plateaus in isolation. They lacked a unified model to link these submerged fragments across millions of years. Magnetic anomalies and crustal data provide the missing connective tissue. These models bridge gaps where physical observation fails. They illustrate how the land rotated and stretched while shifting toward warmer latitudes. The delay in naming was not a failure of field discovery. It was a result of the continental limits lying entirely underwater, proving the connection required decades of accumulating disparate geological evidence. Now, the continent sits restored in these digital renderings. Yet, this geological architecture dictates more than just the shape of the seabed. Its long isolation beneath the waves dictates a history of crustal separation. As the continent transitioned through varied geological environments that locked physical evidence within the strata. Understanding these shifts remains the next hurdle in confirming the true extent of the sunken landmass. To clarify this further, the absence of a formal, global governing body for classification creates a persistent scientific challenge. Researchers must build consensus through data alone, lacking any singular committee to validate the continental status. The geological classification challenge rests on the physical data retrieved from the crust. By focusing on the seismic velocity and the thickness of the underlying rock, the team avoids the ambiguities of surface features. Establishing the continental boundaries requires separating the crustal integrity from the overlying sediment, which often obscures the original tectonic signal. Every drill core and every bathymetric map reinforces the same physical conclusion. The structural properties of the plateau align with those of established continents, regardless of the turbulent history of the surface. This mechanical evidence forms the foundation of the current argument, anchoring the tectonic identity of the landmass in objective physical criteria. Geological identity does not arrive by decree. No governing body sits in session to certify a continent, nor is there a stamp of approval for a landmass of this scale. The process relies on rigorous publication, critical peer review, and the consistent use of data by the scientific community. Recognition is a threshold crossed through the accumulation of evidence, but classification becomes a distinct problem when the subject remains hidden under kilometers of water. Data must speak where the eye cannot see. Critics demand clear, measurable boundaries and specific crustal signatures. If the evidence for a unified block is sufficient, the name gains permanence in textbooks and mapping. The challenge is to prove that Zealandia functions as a default unit despite its fragmented, sunken state. Testing this hypothesis requires applying standard continental criteria to a realm that defies traditional observation, holding the findings against those very thresholds. The data resists the ambiguity of a simple map. With an area of millions of square kilometers, the region dwarfs the scale of recognized microcontinents. The granitic signatures and crustal thickness provide a measurable physical foundation that defies the limitations of mere proximity. Boundaries are clear where the oceanic basin meets the continental slope. The absence of a global governing body to assign the label of continent changes nothing. The identity of a landmass is not a bureaucratic decision. It is a geological reality determined by composition and structure. Science relies on consistent evidence, not an institutional decree. When you remove the veneer of the modern coastline, the fragments coalesce into a single, cohesive unit. The evidence sits beneath the water. The debate now rests on the synthesis of these findings. The sequence of stretching and subsidence reveals the history of the eighth continent. The mystery of its survival is no longer a question of whether it exists, but how the Earth obscured it for so long. The following chapter reconstructs the precise sequence of events. Frames used: Tectonic map ovor, crustal cross-section, seismic density visualization, granite distribution map epithets used, tectonic foundation, geological reality, eighth continent, beginning with the tectonic map, ovor and crustal cross-section, The precise sequence of events reveals that Zealandia never suffered a singular, catastrophic collapse into the depths. The transformation of this landmass was a drawn-out consequence of physics. Deep crustal stretching during the late Cretaceous compromised its stability. As the fragment pulled away from the Gondwana mass, the rock grew thin and lost its natural buoyancy. The subsequent cooling of the mantle and tectonic adjustment pulled it down. Millions of years of isostatic settling finalized the process. Today, most of the continent remains shrouded under the Pacific waves. Yet the continental record persists in the bathymetry and the ancient granitic foundations that hold firm, visualized through the seismic density visualization and granite distribution map. We no longer look at the seafloor as a void, but as a sunken architecture defined by this tectonic foundation. By aggregating this submerged continent final model, we define the geological reality of the eighth continent. This hidden chapter confirms that the map of our world is officially incomplete. The global map now accounts for the vast expanse hidden beneath the Southwest Pacific. The assessment provided the metrics needed to certify these coordinates as continental crust. Zealandia carries the granitic chemical signature of an ancient, stable foundation and possesses the density to remain elevated above the deep-sea abyssal plains. Modern geological scrutiny rejects the need for a central administrative committee to validate its status. Peer-reviewed evidence of crustal composition forces this reclassification. We now view the Pacific not as a seamless basin, but as a sea partially covering a submerged landmass. Future research will address how isolated lineages evolved across this drowning archipelago, a story distinct from the tectonic evidence confirmed in these layers. The seafloor is no longer a featureless void. It is a proven, default structural entity that has persisted through 80 million years of cooling. Earth's surface geography is significantly larger than our visible coastlines admit, as a massive submerged architecture remains our planet's eighth continent.